Hi guys, how are you? Today's discussion about the welding distortion control. So this is a very important subject, welding, and it's always happen the distortion if you are not controlled properly. So how we have to control the distortion for welding, we need to know. So today's topic is welding distortion control. So what is distortion? So we need to know with a very well distortion. Means if you have any object or any plate is there and after certain you are giving any heat or if you give the mechanical force and there is a certain changes is there, that is called distortion. Means undesirable changes in original shape is called, if there is, if by force or by heat there is a changes in the original shape, that is called the distortion. So you see the before distortion the plate is like that, and the after distortion is the plate is like that. So distortion occurs due to heat input and mechanical properties. So distortion, what is the reason of distortion? Distortion the reason for due to heat input and the mechanical forces. Experiment number one you can see here. This is the one is the dot area is mentioned here is the main plate during heated condition. Okay, this is the plate original condition. Uniform heating of a steel bar throw out of its entire volume. When you are giving heating, you see the this is the expansion is going on at it comes up to the dotted condition. Considerable expansion and that takes place in the uniform heating in the all area. Now if cooling of the bar is allowed, if the uniform cooling is happening, is allowed evenly, return this is original shape and size without distortion. So if you are giving uniform heating in the all area in plate or any of the object, it's going to the uniform expansion and uniform contraction. So there will not be any distortion. So what we can say? We can say uniform heating and cooling of the component that can expand and contract that does not cause any appreciable distortion. Once there is a uniform heating and cooling of the component, it's happened, but there is not any distortion will not come in. The plate will be in the same shape. It will become after cooling. Experiment number two, you see there is a clamping jaws is there, and the two sided clamping jaws is there, and the object is inside the clamping jaw. Still work before heating. So before heating, this is the original shape is you see can dot dot. It's actually properly fitted in the jaws. When you are doing the heating, it can't expand because it's inside the clamping jaws. It's restrained the heating. It restrained the expansion. But when you are doing cooling, you see after cooling, the plate it's not in original shapes. Means it's freely it comes under the jaw. So it's called the distortion. So resistant expansion, but in the cooling, there is a change in size, change in shape and size after cooling. So we can conclude that restraint hinders pre-expansion and contraction and cause material to deform, resulting in distortion. So restraint hinder the pre-expansion. The restraint, there is a restraint of expansion but contraction and causes it cause maybe it's called the distortion. Heat input we can the two its heat input we can divide it in the two points in gas cutting heat input and the welding. When you are doing welding, there is a heat is generated, and the gas cutting and heating it also heat is generated. Now distortion in case of spot welding, there is a spot we are doing the spot welding. So heating, when you are doing heating, heated area expand. Okay, heated area is expanding. Expansion restrained by surrounding solid. So expansion restrained, expansion restrained, response cannot be done to restrain the surrounding solid area. Compressive stress or develop, there is a compressive stress is developed. Furthermore, compressive stress lead to plastic deformation. So after the compressive strip develop, what will happen? There will lead to plastic deformation. When it will be the plastic deformation, definitely metal will be bulge at the spot towards at heat sources side. So the source side is the bulging will be done where the heat sources side. So sources side from the heat sources side will be the bulge. Now distortion in case of spot heating. In the cooling condition, spot area tends to contract. It will be contracts tend to contract. Contraction descend. Contraction is restrained due to by surrounding hot area. Material goes back to the original position. So it will be the go to the original position with plastic deformation and resulting will be distortion. So in the spot heating and spot cooling, there is two areas you can the distortion will be occur. This is one of the welding wheel is the longitudinal direction is the welding bed is this. You see, the first is the dotted condition is the original shape of the weld. When you are doing welding, the expansion will be generated. Okay, the expansion will be generated, the heat will be generated if there is a proper not support. If it is not supported is properly, then you can see there is a distortion with the its plates is come inside the from the original shape, and it's also come from original the left and both side. Okay, this is after welding it will be happen. It's a long, this called the longitudinal distortion. Distortion in butt weld. Okay, so it is contraction along the length of the weld bit. So it is a contraction along the length weld of the weld bit. Yes, it is maximum along weld bit and decrease the points away from the bit. It is maximum along the weld bit. Yes, and the decrease the point away from the bit. In carbon steel of cell, it lead to reduction in diameter at the weld. Longitudinal shrinkage, how we can, there is a calculation the part welded in CS, okay, or low alloy steel. This is longitudinal shrinkage equal to 3 dot I dot L divided by 1 log feet 1 log T. What is LS means longitudinal shrinkage, I means welding current, L means length of the weld, and T means plate thickness. So we can get the shrinkage in this formula. Example of LS in bar 12. Calculate LS for 6 thickness CS plate welded by SMW using 200 A current. So solution is longitudinal shrinkage equal to 3.200 3.200 divided by 1 lakh into 6 L by 1011 L by 1000 mm. So this is the longitudinal shrinkage in the bar 12 in the formula. So longitudinal shrinkage is B fillet weld. L is equal to 25 AW or AP. Okay, then AW equal to what is this AW? Weld cross sectional area, and AP means resisting cross sectional area. What is AW? You see AW, this is the AW, this is the black one, and the AP in the cross marks, the hazy mark, this is the resisting cross sectional area. Example of longitudinal shrinkage fillet weld. You see here 6 mm plate thickness, 75 is the T height. Okay, 8 into 8 in the fillet weld joint, 6 mm is the thickness. So all dimension is you can if you go the formula, it is the longitudinal 1.52 mm. Distortion in butt welds. Okay, then transfer that distortion. That is called the longitudinal distortion, and this is the transfer direction. It is the shrinkage perpendicular to the weld. That is the longitudinal, this is the perpendicular to the weld, the transfer direction. It leads to development of high residual strength and also cracking in case of highly restrained joint. If it is highly restrained joint, then it will be high residual strength and definitely crack will be occurred. It is not uniform along the length of the blade. It is not uniform transfer direction. It is not uniform along the length of the blade. It is laser at the end of the plate where bead is started. You see here is mentioned the transverse distortion. Transverse distortion is the weld bead. This is the weld bead. Weld bead is their original position is there. After welding, it's going inside, and this is the transverse direction. So transverse direction is there in the original direction. This is the transfer, and this is the longitudinal. Transverse shrinkage in single pass bar joint. So this is the longitudinal singeage formula. This is the S equal to 0.2 AW divided by T plus 0.05 T, where A is equal to transverse singeage, AW means cross-sectional area of the weld, T means thickness of plate, and the root opening is mm. So you can get this one, this formula, the transverse singeage. Just there is an example that I know that during multi-pass welding. So this is the sinkage. This is the transfer sinkage for single pass bar welding. Now this is the during the multi-pass welding. What is the formula? TS equal to TSO plus B log W minus log W0, where T is total transverse sinkage, TS0 means transverse sinkage after fast pass, W means total weight of old metal, W0 weight for fast pass old metal, and the B is the coefficient. So this formula we need to know the for to make the to check the transverse sinkage or the longitudinal sinkage. So effect of various procedure on transverse sinkage pattern. What is the effect? The effect on various procedure. Procedures is root gap. Okay, root gap procedure. TS increases with increasing RG. Joint design single V produce more transverse sinkage than double V. Okay. Electrode dia. If TS decreases with with increasing electrode dia, transverse sinkage will be decrease in case of electrode dia. Degree of constant. Transverse sinkage decrease with the degree of constant. Pinning. Transverse sinkage decrease by pinning. Gouging and repair. Transverse sinkage increase by this operation. So whatever the effect will come for this particular root gap, joint design, electrode dia, degree of constant, pinning, gouging and repairs. What will the effect for the transverse sinkage? So it is explained here. Transverse sinkage in fillet joints. Transverse sinkage leak of the fillet well by bottom plate thickness into 1.02. This is the transverse thickness of the fillet joint. It is TB. This is the bottom plate thickness. 1 into 1 is the fillet weight length into 1.02. Transverse sinkage in fillet joints. For intermediate fillet, a correcting factor of proportional length of fillet weld to total length of weld length of joint should be used. So transverse sinkage of fillet joint for intermediate fillet joint, a correcting factor of the proportional length of fillet joint to total length of joint should be used. Now you see transverse sinkage in fillet joint. The fillet weld in a lap joint between the plate in equal thickness, two welds is there. One, this is the TT. So transverse sinkage will be leg of the fillet weld. What is the leg? Leg is the this is the fillet weld leg, and that is the plate to thickness. This is T into 1.52. This is the transverse thickness of the fillet joint in the lap condition. This is the angular distortion. This is the original position. When you are doing welding, then it will be the expansion will be there, and it comes from the original position, because the heat is coming here. Okay, heat is coming here in the surrounding the welding condition, so it will become expansion, and the after contraction it will not come to the original condition. Distortion in bar weld. Angular distortion. It is the bending transfer to the weld. So it is the bending transfer to the weld due to the non-uniform heating and cooling along the thickness of the plate. So in the transfer direction, if you go, there is only one the middle condition we are doing welding. So this is the uniform not heating. So because of the non-uniform heating, this causes to the distortion. This is the main source of mismatch and dimensional accuracy in the large welded structure. So always you can see in the older structure, this is the main problem in the mismatch or some dimensional problem in because of the distortion. Angular distortion in bar joint. Use both side welding technique in place of single sided welding. It is the T1 plus 1 by 2 T3 by T equal to 0.06. So it's mentioned G here is the gap, and G equal to 3 mm and T3 equal to 2 mm. So angular distortion in bar joint, this is the formula. Now angular distortion in the fillet joint, you see AD equal to 0.0076 point W and point into 1.113 t square. Okay, so now it is W. When you are doing welding here, it comes under inside because of that there is no in the opposite side there is no support. So that's called the distortion. Where AD equal to angular distortion. You see here W equal to flange width. Okay, L equal to weld length, or and the T equal to flange thickness. Now example of angular distortion in fillet weld. Example of angular distortion of fillet weld. If you angular distortion in fillet weld also here, find the angular distortion in double fillet weld of a T joint. This is the double fillet weld. Here is the T joint is there. So what will happen? The fillet joint is between a flange 100,000 mm wide and the vertical member when the thickness of the both member is 6 mm and the old leg is 8 mm. Solution equal to AD angular distortion 0.0076 into 1000 into 8 to the power 1.3 divided by 6 square equal to 3.515 mm. This is the angular distortion of fillet weld. This is the one side and another is the double side. Then multiple resistant fillet weld. Then the multiple resistant fillet weld. If you see here, ED equal to AD by L 1 by 4 dia minus X by L minus 1 by 2 square phi. So AD equal to angular distortion, L equal to span length. What is the span length? L. Phi equal to angular changes. Okay, radians. What is the angular changes? X equal to distance from wheel to the point. What is the distance? X equal to distance from the wheel to the point where distortion is to be determined. So this is called X. Example of ED in multiple resistant fillet weld. In multiple resistant fillet weld, the span length is 1 meter and the angular changes is 9 degree at a distance of 400 mm from the span end. Find the distortion. So is the same will be applied by putting L equal to 1000 mm, phi equal to 9 degree 0.157 rad, x equal to L by 2 4 minus 400 mm in the formula. So AD will be in this formula. If you can apply in this formula, this AD by L. So it from here you can find out the AD equal to 14.164 mm. So this is the all example you can find out the multiple angular distortion. This is transverse sinkage and this longitudinal how you can get the actually from the formula. Now distortion in T joint. How it is coming the angular distortion. It is before welding like this and after welding it comes on the same. Same it is the uniform. The uniform heating is not there. So it comes under like this angular distortion. This is called the T joint. Distortion of T joint is a longitudinal reduction and this is for the angular distortion. This is a longitudinal distortion pulling effect towards neutral axis. So it is the two sides. This is the two sides fillet weld. This is called the pulling effect towards neutral axis. This is longitudinal distortion. Distortion of T stiffener. Longitudinal distortion is the T stiffener. If you go the stiffener is there, pulling effect of the oil above neutral axis. So this comes on the longitudinal reduction will come. Now we find out the so many distortion is here from the longitudinal distortion, transverse direction, transverse distortion, then fillet weld distortion, then angular distortion. So now we'll go the to prevent distortion. How we can prevent the distortion, reduce the effective sinkage force. How we can prevent? Reduce the effective sinkage force. Keep the angle of the weld joint to the barest minimum. So minimum angle of joint as per WPS we have to follow, not by the maximum. Keep the angle of weld joint 45 degree. Minimum angle, less welding, less input, hence less distortion. So you have to very careful. Minimum angle, it will become less welding will be there, less heat input will be there, and the hence less distortion will be occur. So the first is reduce effective shrinkage force. Keep the angle of welding at barest minimum. Reduce the effective shrinkage force. Reinforcement. requirement. If it is reinforcement requirement, it is 20 mm plus plus 20 20 mm plus minus 5 minus 1. Keep reinforcement up to 19 mm. Okay, minus 1. So do not keep root gap more than required. If it is required in WPS 1.5 to 2 mm is the root gap, so we have to follow the 1.5 to not more than 2.5 mm. So the distortion will be occur. Do not do overwelding. Don't do overwelding. Overwelding it can cause the more distortion. You see here 7 mm plus 3 minus 1. Here is 19 mm plus 3 minus 1. Keep fillet size 18 mm by 6 mm. Okay, keep 18. So here is minus 1. So you can measure it. You can keep here 18 mm and 7 mm plus 3 minus 1. So 6 mm. So you have to use the minimum one and the actual one as per the WPS, and we are qualified in which requirement. Keep the angle well joint. Keep the angle well joint is 45 degree. 50 degree plus minus 5 degree. So 45 degree is the best one, best option to prevent the distortion. You see, reduce the effective shrinkage force. Minimum no number of passes larger of the electrode, larger size of the electrode. So if you do the larger size of the maybe 40 mm electrode, so passes will be the less. Then distortion will be occur less. Because if you do the more passes, the more heat input will be occurred and the distortion will be again happen. If it is a maybe 2 mm welding, then more number of passes will be required. The less number of passes is the so larger size of the electrode. So reduce effective shrinkage force. Plate welds near the neutral axis. So plate weld always do the it should be the neutral axis. If you do, then the effective shrinkage force will be less. To prevent distortion, make shrinkage work for us. What will be the shrinkage work? Be make shrinkage work for us. So this is pre-cambering or pre-bending implant. So clamps along the edge. Here is the clamp is there, wedge is there. So this is if there is a clamp and wedge is there, so there will not be any distortion because it's restrain the contraction expansion. Make shrinkage work for the keep over dimension or over bend before welding. So if you do there you know that this side is the one side is it will be the welding will be welding will be done and the other side, so you can bend a little bend, so after welding it will be the in the same condition, but it is not the proper practice in this industry. So you have to give in this other way to give the one support, so it cannot be done the contraction and the construction. Balance linkage force with other forces, so we have to do balance linkage, so contraction and the expansion it will be the balance. So how we can do, you see here balance linkage forces with other forces. So if you do, you see here the sequence welding 1 2 3 4 5 6, so this is the sequence welding, and if you go there the right hand side 1 2 3 4 5 6, this is the best way to shrinkage force in the balance way. Balance linkage forces with other forces. Back step welding, if you go the back step welding progression in the back step welding, so one is first, then two, then three, then four. This is a back step welding, balance linkage welding. Back to back clamping, if you are doing on welding, if the back to back clamping is there, if it is there is a clamp you have arrange a clamp or jaws or back to back welding, then this will not be happen. You see here back to back welding of saddle, so back to back welding is saddle, so this welding tax is there 1 2 3 4 5 6, so it can restrain the distortion. Okay guys, so this is one of the very good topic about the distortion from the beginning to end. What is distortion, what is the type of distortion, how we can prevent the distortion, how we can measure the distortion. Okay, So I think everybody gone through every point and everybody understand. If you have any query, if you need any, if you have any asked question, you can just comment on my YouTube comment box. Okay, again, thanks for watching. Bye bye.